All right. So on Monday, because on Wednesday we had Cody come, we looked at the force, electric force being R K Q1 Q2 over R squared. And this force is a field force, so it's in the direction of my R. All right. And this is going to be based on individual charges. And we looked at problems where we had a positive, a negative, and I'll do a negative. And if I wanted to look at the force on this one, these two are going to repel each other. These two are going to attract each other. So if I'm looking at the force on that one, we know it's going to go in that direction. And we could play with our sum of our forces. And we looked at forces in terms of different geometries. So I could do a negative, positive, let's do a positive. And so if I looked at this one and I wanted to look at the force on that one, we know that this one, we've got this part here, and then we would have, oops, no, I'm going the wrong direction. We're going to make this one negative and negative. So so all of these are negative charges. So those are going to repel, and these would repel. So the net force on that one is going to be the sum of those two particular vectors. When we first introduced electrostatics, we talked about that I was going to draw a field force, and we could represent our field forces with field lines. So that would be my electric field force around a positive charge. And if I had a negative charge, we indicated that my field lines were going to go towards the negative charge. Okay. So now let's go back and let's look at gravity for a minute. So if I have good old planet Earth, and we now have, we're going to draw gravity as a field. Some things that we know is if I take my object and I move it up to a new height here, it's still going to be attracted towards the center, but I've done something to it. Okay. We've done something to it, and we've looked at our gravity. And if we look at Newton's law of gravitation, remember it's big G, mass 1, mass 2 over the distance squared. But if I'm dealing with a little mass, something the size of a golf ball around the surface of the earth, that's a pain in the tushy. We still have our force is going to be directed towards the center, but this could be rewritten as mass of the earth, radius of the earth squared times my secondary mass. And that gave us our acceleration, And we could play with that. Okay, we could play with that. So I could actually write things in terms of my gravitational force here, in terms of this, and that gave me my acceleration that I want to deal with. So we could play with that, right? We could play with that. The thing about this is, though, I get away with this, and this is our acceleration due to gravity, which is a g, but this starts to being near the surface of the Earth. Well, if I were doing this around my sun, the big sun, S-U-N, Sol, if I do it in Espanol, or Sud, if I do it en français, we get the idea that I could represent this as a field object, okay? And it may be more conducive to be playing with something like this. So what we're going to do for electric fields, we're going to define an electric field. And we're going to define my electric field as my electric force divided by Q, where that Q is my test charge. And just like what we saw back in mechanics, the force is going to be, the force and acceleration are along the same lines. So I'm going to define this thing called an electric field. Now, what that means is, so if I have a positive 90 nanocoulomb charge, and I have a negative 60 nanocoulomb charge, and the distance between these puppies, we're going to make that 1 meter just for excitement's sake. Here's my test charge. We can calculate an electric field at that point, so that all I would have to do to find the force on the charge is whatever test charge I put in that, whatever magnitude of that test charge I put in that, I can get and represent my electric field. So what this means is, this is going to be K Q over R squared. So we can calculate an electric field, and if I go ahead and give myself a distance here, and we're going to be nice, we're going to call that 1 meter. That's going to make life really easy, because then this distance is the square root of 2, right? And this distance is the square root of 2. The other assumption that we make is that the test charge is positive. That's the other assumption that we make. So this problem is going to work very much like the other problems that we did. So if I want to know what the electric field is at that point, I'm just going to calculate the electric field. Calculate, I was doing forces this morning. I'm going to calculate the electric field due to the 90 kilo or 90 the 90 nanocoulomb charge, so that's 9 times 10 to the 9 times my 90 times 10 to the minus 9, all divided by the square root of 2 squared. It's going to equal I get 405, and that is going to be, E is going to be in Newton coulombs. If I calculate the E, and that's going to be this one of the positive chest charge, so this is going to want to go in this direction. Nope, sorry, I am backwards today. This is going to want to go in this direction.
You said that test charge is positive?
Yep, test. No, I was doing it right then. Until it's Friday. Yep, it's going that direction. And this one is going to go this direction because it's negative. So our resultant electric field is going to go out somewhere in that direction. We can calculate our 60 nanocoulomb charge. I get 9 times 10 to the 9th. And I get 60 times 10 to the minus 9. And it's also divided by the square root of 2 squared. This becomes, we can also simplify and not have a calculator problem. So I got 9 times 60 divided by 2. Because that zeroes out. This gets 270 nanocoulombs. Now, those are the magnitudes, right? So we got to play with our angles and all that other good stuff, but we can just sum them up at that point. And we know that our resultant is going to be going off in this direction somewhere. So these problems work the same, but once I get my electric field, so don't be fooled. Somebody might give you that my electric field can be represented by 60 I minus 20 J Newton coulombs. What is the force on a, and we'll do the magnitude of the force. What is the force on a 30 nanocoulomb charge? Force is going to equal QE. So all that's going to be is 30 times 10 to the minus 9. 60 I minus 20 J. That's in coulombs. I'm in nanocoulombs. My coulombs cancel out, so my unit analysis helps me out. I'm going to have 1800 times 10 to the minus 9 I. I'm going to have 600 times 10 to the minus 9 J. And of course, you can simplify that. But the thing is, don't overcomplicate stuff. We get this all the freaking time. You sit there and you try to do a big, huge calculation, and you're going, oh my gosh, all I had to do was deal with that. And you can actually simplify things. Now, how are we doing? Oh, good. your book, okay, in this chapter, we'll go in and look at dipoles. And dipoles are those things that we can draw field lines from it. We're always going to draw from positive to negative. Your book goes through and really concentrates on field lines. Because what we're going to end up doing with field lines is we're going to use those field lines so my dipole is going to look like that. But what we're about to do in a little bit is we're going to use those field lines to help us out for something else. And we're going to look at things that are perpendicular to our field lines. And the red lines are lines of equal potential. And we're going to get to potential next week. But these are easy to measure. And we can actually measure lines of equal potential. And then we can infer our electric field lines. Which is a little bit different if I were dealing with magnets, because if I were dealing with magnets and I set out my iron filings, we see those field lines and not the lines of equal potential. So those are a couple of different things that are there. Now, this is engineering physics. So usually we stop there for general physics, but engineering physics, we get to look at a bunch of different things. So I have a wire. Okay, and we can think of a wire as a distribution of charge. So I can look at this as an incremental piece of charge. So if I think of this as a distribution of charge, I can look at an incremental piece of charge. And that incremental piece of charge is going to look like a linear charge density. Times my incremental length, because I can look at that as a little piece of length of my charge. I can look at my overall charge, right? And now if I want to do an electric field at this point, and we're going to set this up, so this is L over 2, and this is L over 2. And I want to calculate the electric field at this point due to that distribution of charge. We can look at our incremental piece of electric field. That's respect to my K over R squared dq. Because what we're going to do is we're going to sum up all of those little itty bitty bitty teeny tiny pieces. Right? We're going to sum up all those itty bitty teeny tiny pieces. So what we can do here is we have a piece that's there. We've got that angle that goes from there. And we can, the tricky part about all of this stuff is that, I'll make sure, is how we're gonna represent how this moves across. So if I'm looking at this side, okay, I'm looking at this side, we're gonna call this E sub left. And then we're gonna have that side as E sub right. All right, we'll have the E sub left and the E sub right. As I look at this little incremental piece, I can look at DEL is equal to our DEL cosine of our angle in the I direction plus DEL sine of the angle in the J direction. We know that if I do all of that, if we go ahead and look at the right side, okay, this side goes this way, that side goes that way. We're gonna do the right side, I get DE right cosine of the angle, and that's negative. And this side is DE right sine of the angle. But the magnitude of EL is equal to the magnitude of E right. So DE is just going to be 2DE, some little component here. And that, of course, we can get our DER is equal to KDEQ over R squared, but R squared is going to equal X squared plus Y squared. So I'm going to get KDQ over X squared plus Y squared. So what happens with this is that your tough part is setting up those little incremental portions of your line of charge. And then we can set up our integral. It's going to go from 0, or we can go from minus L to L, but it goes from 0. Oh, let's do it from minus L to 0. And I get 2K YDL. And so that gets us into that part. Sine of the angle, by the way, just to remind everybody, sine of the angle is going to be Y over X squared plus Y squared to the 1/2. So we're going to put this part in. So there's our 2. There we got that. We've got that. So this is going to be X squared plus Y squared to the 3/2. And then you just, well, you'd integrate it and you'll ultimately get KQ over Y 1 over the square root of L squared plus Y squared in the J direction. And this, by the way, is section 24-6, and it's example 24.4 in your text. But you can do it for a ring of charge. You can do it for a sphere of charge. You can do it for squares of charge. You can do it for a variety of different ones. And they do the ring of charge one, by the way. The ring of charge example is example 24.5.
Can you show what DER equals real quick?
Do what?
Can you show what DER equals?
That right there? Hang on. That right there?
Yes, thank you.
I don't have time to do anymore. Because some of you have another class at 1:30.